Alright, this is Ken Roosevelt, and this is Central Limit Theorem 2010 Part 4. In the last video, I hope that you noticed that we can't use the same formula all the time, and that the Central Limit Theorem only applies when we're looking at means of populations. And now I'm going to try to do one of these in Alex with you guys. And then I'm going to bed. Alright. The mean salary offered to students who are graduating from Coastal State University this year is $24,260 with a standard deviation of $36,078. A random sample of 85 Coastal State students graduated this year has been selected. Graduating this year has been selected. What is the probability that the mean salary offer for these 85 students is $23,500 or more? Now, notice with me that they don't tell us anything about the distribution being normal. And because they don't, we need a minimum sample size of 30, and we have a sample size of 85, so we're okay. Since they're interested in the probability that the mean, that's important, it's the mean salary, not an individual salary of one person they pick out, but the mean of these 85 students is 23.5 or more. We're going to use the central limit theorem. So the formula we're thinking of, let me put it over here, is z is equal to x bar minus mu over the standard error, which is sigma divided by the square root of n. So what I'm going to do is first I'm going to start with x bar. My x bar that I'm trying to check on the z value for is 23,500. I'm going to subtract that from that the mean, which is 24,260, and I'm going to divide that result by the standard deviation, which is 3678, divided by the square root of the sample size, which is 85. And I'm going to tap out of that and close that parenthesis. Now that'll give me my z-score. They want to know what's the probability that the mean salary offer for these 85 students is 23.5 or more. So actually what I can do is, I wonder if it'll let me do this. No, it won't. So I'm going to have to wait till I get my answer. I should have done this before, but I'm going to get my z-score. Here it is. It's negative 1.9. Does that make sense? Yeah, because 23.5 is to the left of 24,260, and is significantly to the left when you consider the standard deviation is only like $3,500. So now I'm going to use that. I'm going to find the z-score to the right, or to the left of that, but they want that or more. So if I was drawing a picture here, and I probably should, but I don't feel like carrying this into OneNote and going through all that. So I'm just going to tell you the shading that is called for in the problem is to the right of this 23.5, but the probability that they're going to give me here is to the left, so I have to subtract that from 1. And when I do, I get my answer is 0.9716. And that's what I'm going to put in here. 9716 is actually 97161, so my rounding is okay. 971, I missed the 16. I don't need that extra 1 there. Okay. We'll do another one. A worldwide organization of academics claims that the mean IQ score of its members is 115. Ooh, so smart. With a standard deviation of 17, a randomly selected group of 35 members of this organization is tested, and the results reveal that the mean IQ in this sample is 116.4. If the organization's claim is correct, what is the probability of having a sample mean of 116.4 or less. All right, so they're claiming their mean is 115. They want to know what's the probability of this happening or less. And first, again, we have to find the z-score. So we start with the x-bar, which we're testing here, which is 116.4. We're going to subtract from that 115 to get the difference between that value and the mean. And we're going to divide that by the standard error, which is the standard deviation 17 divided by the square root of 35. And because it's 35, even though they don't tell us it's normally distributed, we're okay using this formula. Okay? So I hit enter, and this is my z-score. And since they want to know what is the probability of having this 116 or less, I'm okay just hitting this button here because that'll give me the left-hand shading. And the answer is 0.68694, so 0.6869 is fine. I think with one more it'll add it to my pile. Let's check if I have time. I absolutely do. So I'll do this one more, and then we'll go to bed. The producer of a weight loss pill advertises that the people who use the pill after 1 week, that people who use the pill after 1 week and average, lose, okay. That people who use the pill lose after 1 week an average of 1.8 pounds with a standard deviation of 1.05 pounds. In a recent study, a group of 60, see, we don't even need to know if it's normally distributed. We have a appropriate sample size. A group of 60 people who used this pill were interviewed. The study revealed that these people lost a mean of 1.9 pounds, so better than their claimed average after 1 week. If the producer's claim is correct, what is the probability that the mean weight loss after 1 week on this pill for a random sample of 60 individuals will be 1.9 pounds or more? So again, we find our x bar is 1.9. But since they're saying 1.9 pounds or more, I'm going to go 1 minus P of z. Okay? P of z less than whatever. And now in here, I'm going to do all this in one step. My x bar is 1.9. My mu is 1.8. I am dividing all that by my standard error, which is 1.05 divided by the square root of what's my sample size? Sorry, 60. Tap out of that, close that parenthesis, and that looks good. Enter. The answer is there's a 23% chance of having higher weight loss than 1.9 pounds per week. 23.034, we'll just put 23.03, and now we're done. And I hope that's straightforward and simple to you, that you understand how to do it. In real life, it's a little more difficult because you have to recognize when they're asking about an individual and when they're asking about a mean, when it's appropriate to use which. And also you have to recognize when it's likely that you'll have a normal distribution and when it's not. When it's not, you definitely need 30 or more in your sample. But when you know it's something that's normally distributed or approximately normally distributed, you can get in on this for no matter what the sample size is. You're allowed to use the central limit theorem. Having said all that, I will now say good night. All right, bye-bye.